Good morning, ladies and gentlemen. Today we'll be talking about solubility. We talked a little bit about solubility last class. Solubility is how well things kind of dissolve, right? And we talked about what happens when things dissolve, and that's what we practiced last class. What happens when you put a solid into water and it breaks apart. So let's just review a couple of examples that we worked on last class. All right, so if we take this example right here, we have this compound, ammonium carbonate. And if we take this ammonium carbonate compound and we put it into water, what will happen to that water? I mean, what will happen to that compound? Well, let's take a look. So we take the ammonium carbonate, put it into the water is going to dissolve this solid. You're not sure why, but we'll talk about that today. And it's going to break apart and it's going to form NH4 plus, another NH4 plus, and that CO3 2 minus. How do we know that? Well, because we know that carbonate has a 2 minus charge, and we know that each ammonium has a +1 charge. Whoops, I didn't put a plus there. And these two pluses balance out that minus charge. What would that look like? That would look like this. We'd start off with NH4. Oh, let me get this back. All right. It would look like NH4 CO3. Okay, NH4 CO3. And that NH4 CO3 is going to break up into 2 ammoniums and a carbonate. And this is how this equation would look. And let's take a look at this one over here. This is sodium phosphate. So we have 3 sodiums and 1 phosphate. When we're on the periodic table, here's our periodic table. The first column, ladies and gentlemen, has a +1 charge. The second column is a 2+ charge. Third column is a 3+ charge. And then we have the transitional metals. Then over on this side, you start off with 0, -1, -2, -3, etc. Sodium is in the first column. So sodium has a +1 charge. Phosphate, we know by looking at our common polyatomic ion sheet, it has a -3 charge. This is going to break up into 3 Na pluses and 1 PO4 3 minus. And notice that the 3 minus charge is going to cancel out those 3 pluses and vice versa. Now, something that some people do, and it's incorrect, is they'll write Na3 plus. That's wrong. Each sodium is an individual piece, an individual ion. So this is how we'd write that out. And then if we come down this way, I'll just highlight this whole thing right now, unhighlight it. You'd end up with sodium phosphate will break up into 3 sodium ions and 1 phosphate ion. So this is how we did our homework last time. Hopefully everybody has that. The homework that we did complete looked very good for the people that turned it in. So let's move on. So today's lecture is going to be talking about solubility. So let's just talk about what soluble means. Soluble, ladies and gentlemen, means the ability basically to dissolve in water. So dissolving in water is soluble. So if you put salt in water, salt kind of disappears to where the container just looks like regular water. Something that's insoluble does not dissolve in water. And those things, if you end up with something insoluble, usually you'll have a pile of the stuff on the bottom, right? Or the solution is going to be super cloudy and you'll be able to see the particulate matter. So those things are insoluble. And we went over some examples like muddy water is not soluble, right? So rocks and water aren't soluble. And we'll talk about those things today. Lastly, let's review the word aqueous. Aqueous just means dissolved in water. Dissolved in water. And there's lots of ways for us to show this, but one thing, for example, let me scroll up the page a little bit. Let me see if I can scroll up there. There we go. So Yeah, I'll just rewrite it. So if I would write, let me just get rid of everything here. So if I would write, ladies and gentlemen, a container, if I would just say I have NaCl and I have solid NaCl and I put it into the water, and we discussed it's going to break apart into Na plus and Cl minus. This is dissolved, and we would say this is an aqueous solution. Aqueous means dissolved in water. So at this point, this would be NaCl aqueous, where this is NaCl solid before we put it into the solution. Then once it's in the solution dissolved, we say aqueous. So basically, aqueous is dissolved in water. That's its definition. All right, so let's move on. So what compounds are soluble in water? Well, that's the whole point of this lesson today. We want to find out what dissolves and what doesn't dissolve in water when we're talking about ionic compounds. And that's what this says. We'll be able to determine what dissolves. So will salt NaCl dissolve in water? Well, we're going to take a look at that. We already know salt does dissolve in water, but we're going to see why it dissolves in water. All right. So first, let's take a look at water molecules. All right. Now, yeah, I got it all on the screen. Good. So these are some water molecules, ladies and gentlemen. We haven't really taken a look this year at what water molecules look like, but we know that water, well, most of us know that water is made up of H2O. So H2O, 2 hydrogens and 1 oxygen. This is our water molecule. And what it kind of looks like is the 2 hydrogens are off to the side, and we have this central oxygen. This is usually how you'll see me drawing water. You'll see me drawing the 2 hydrogens and the oxygen in the middle. Well, what's so special about that, ladies and gentlemen, is that the oxygen holds this negative charge, and the hydrogens hold on to these positive charges. And this makes water, it's called a polar molecule, which means that there's an unequal distribution of electrons and all sorts of other stuff going on. But the idea is that different parts of the water molecule are positive and negative. Now, this part down here, basically, if you would just draw this, I would sit here and say, this side, this is a partial, it's a Greek delta, that's partially positive. And this side up here is partially negative. Oxygen holds the negative, the hydrogens are more positive. And so what that allows is for water to rip things apart. And everything we're going to talk about today is going to be about love. All right. But we have to understand how magnets work. So if we take a look at magnets, ladies and gentlemen, you understand that there's a north and a south side of magnets. So let me see if I can get this close. All right. So I'll put this up. So you're looking at this little tiny screen. This is a pencil that I'm holding in my hand right here. All right. And I'm going to take these magnets. I'm going to put this magnet. You see that all these magnets are stuck together. But if I take these magnets, right, and I put them on this pencil, you can see that there's a gap. There's no trick right there. There's a gap between those magnets. Why is there a gap there? There's a gap because I've lined up 2 positives together and 2 negatives together. So what would happen if I took a third magnet and put it on? It would kind of hover up here as well. It's just magically hovering. If we turn this magnet around, whoops, all of a sudden, these 2 combine. That means that there's a positive side with a negative side sitting with those magnets. But if I turn them this way, I flip it around, that means that there's a negative and a negative, or positive facing a positive. So working with water, the positives are going to be attracted to the negative. So the negative of this water up here is going to be attracted to a positive somewhere else. And they work very similar to kind of how a magnet works. So let me take you down here and show you a couple pictures. So molecules like water, like salt, they're going to dissolve in water. And they're going to form +1s and -1s. But in the case of silver chloride, ladies and gentlemen, is not going to dissolve. It's going to stay insoluble. Silver chloride stays together sodium chloride breaks apart. You'll be like, but how do you know? Well, it's all about love, ladies and gentlemen. And I'm going to take you to the love right now. So let's just take a look at salt in water. So salt, which is made up of NaCl, you'll have like a little Na particle and a little Cl particle. Water is going to come on in, and water is going to try to break these the salts apart. And if the salt, this case is NaCl, and if the salt starts breaking apart, it's because there's more love or more affinity. There's more love between the water molecules and the individual chlorides and sodiums than there is between the sodiums and the chlorides. So if sodium and chloride really love each other a lot, they will not let water break them apart. But water's always going to be coming in to try to break up that relationship. And if sodium and chloride don't have a strong relationship, which they don't, the water comes on in. Since the sodium is positive, the negative side of the water comes in and takes the sodium. And since the chloride is negative, the positive part of the water comes in and takes the chloride. And you can see that here. You can see that all these blue ones, all these positive hydrogens are surrounding the chloride. And on the sodium, you can see that all these negative oxygens are surrounding. If I said sodium, I meant chloride. All of these hydrogens are surrounding the chloride, and all of these oxygens, which are negatively charged, right? All these negatively charged oxygens are going to surround the sodium. And so that's what breaks apart. And I said earlier, I said silver chloride will not break apart in water. And the reason is they love each other too much. There's too much of a relationship between silver and chloride. They've been too much together. And so when that oxygen comes in, and remember, oxygen is positively charged, that oxygen comes in, right? And then the hydrogens come in to get that chloride, and chloride is negatively charged. So then hydrogens come in there. The hydrogens cannot break that break that chlorine apart. And we're just going to talk about how to find that answer. But this is basically why some things dissolve and some things don't. If there's a strong affinity right here, if these two really love each other, they're not going to break apart. And if they're like, oh, whatever, dude, done, they will break apart without any problem in the world. They'll just dissolve away. All right, so let's continue. Hopefully you got that crazy little story. So this class is coming down to right here. This is the most important sheet we're going to have. This sheet is going to tell you whether things are soluble, whether they break apart. Hopefully you guys can see me. If you're in class, I would say soluble things break apart. Insoluble things are going to stay together. So this is soluble. This is insoluble. This would be like the sodium and the chloride. They break apart. And this might be like the silver and the chloride, and they stay together. So this sheet right here is going to show us how to determine whether things stay together or break apart. And I'm going to show you that now. So I'm going to go over this, this sheet with you. I'm going to move it in a little bit, make it a little bit bigger so we can all see it. All right. And let's see how big I can make this. There it is. Perfect. So let's just take a look at how this sheet is set up. First things first, there are a bunch of different columns, and I'm going to go fast. You guys can rewind this. All right, so that says soluble. This column right here is everything that is soluble. This column over here is everything that is insoluble. Well, soluble means right here, you can see this is soluble. Soluble kind of means to ionize, means to break apart. It means to disassociate. Soluble means the stuff is going to stay in solution. Your hands are going to come apart, and I'm talking your hands are going to be apart. And in theory, there's no reaction going on. So that is what soluble means. So this side over here is all soluble. This other side over here, all right, we'll put this one in blue. This is the insoluble side. And what does insoluble mean? Insoluble means does not ionize, which means does not turn into charged particles. Things stay together. there's a falling out of solution, which means things will go and drop out of solution. And that's what we talked about last time. That's what a precipitate is. Your hands are going to be together. So if I say, hey, what's an insoluble compound look like? You're going to take your hands in class and you're going to put them together and say, this is insoluble. And insoluble things are going to be on that reacting portion. And I'm going to take you through this right now. So these are anions. Anions are negative. Notice that every one of those are negative, 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 negative 2, negative 2, negative 2, negative 1, negative 2, negative 3, right? So all of those things are negatively charged. That's what an anion is. So what we are going to do, we're going to look and say, this, you see how it has like silver ions, lead, mercury, thallium, all of those are in there. And then here we have ammonium, group 1s and group 2s. This is what's reacting. So let's start off with acetate. What can we mix with acetate to make an insoluble compound? Well, there's only one thing. The only ion that we can put with acetate is going to be silver. And if silver gets together with acetate, it's going to move in the insoluble direction and form an insoluble compound. If you choose any other ion, every other ion in the world is inside this box. You choose sodium, Na+. That means if you put sodium ion with acetate, it's going to be soluble. It's going to break apart. So every ion possible is inside of this box right here, except for silver. Silver is the only ion that forms an insoluble compound with acetate. Let's take a look at the next one. Notice iodide, bromide, and chloride are all in the same column on the periodic table. All right, I'm gonna bring out a periodic table for you. Hold on for 1 second. Okay, so I just brought up the periodic table. You can see it over here on the left-hand side. All right, and I'll use that now to work with us. So here we go, iodide, bromide, and chloride. You can see them all right here. Iodide, bromide, and chloride. So we're gonna be talking about these three. And these three, right, are in the same column, which means they're gonna react very similarly with each other, okay? What is gonna react or form an insoluble compound with iodide? If you put silver with iodide and you made AgI, because it's a +1 with a -1, this will form an insoluble compound because the silver is on the insoluble side. So when silver and iodide get together, it's an insoluble compound. What about if we did lead-2 with iodide? Well, if you made lead-2 with iodide, you have a -1 and a +2, which means you'd have to put a 2 there so the charge is balanced. This would also form an insoluble. Insoluble means things are going to be together, right? A lead and iodide will not dissolve in water, all right? So now what are we going to have? Oh, I mixed my colors up, but that's all right. So what is inside of this box right here? Is magnesium inside of this box right here? Magnesium ion? Yes, magnesium ion is in this box. How do you know? Because it's not in this box. Do you see magnesium in there? No, then it's not in that box. It's on the other side. What else would be in there? Well, calcium, strontium, rubidium, potassium, sodium, lithium, beryllium, chromium 1, 2, 3, 4, 5, 6, 7, manganese, iron, cobalt, nickel. Everything else is inside of that box right there. And how do you know? Because it's not in the insoluble box. Let's try another one. Let's look at bromide. What will form an insoluble compound with bromide? Silver, lead, mercury 1, and thallium also will do that. What will form a soluble compound, which means breaks apart? Everything else that's in this box that we just went through. Everything in this box is in that one and that one. All right. Now let's move on. Let's take a look at nitrate. Nitrate, ladies and gentlemen, it says all cations, and remember a cation is a positively charged, all cations are soluble. So every single ion is in this container here, in this box right here, right? See, we're going across. What will form a an insoluble or a precipitate, and it says nothing will form. No cations react. So nitrate will always be broken apart in solution. Chlorate will always be soluble or broken apart. Remember, soluble means breaks apart, ladies and gentlemen. Soluble means breaks apart. All right, let's come on down to sulfide. What will form a compound, an insoluble compound with sulfide? Well, it says it reacts with most cations. So what's in that container? Well, everything except for what's on this side. So what will be insoluble? Well, ammonium sulfide will be insoluble. So if you have NH4, and you would need 2 of them, okay? Sulfide is soluble, which means it's going to break apart and form NH4 plus and S2 minus. And you know that because ammonium is on the soluble side. Be going towards the soluble side. So what would be insoluble? Well, you can see that this says all group 1s. Well, what does all group 1s mean? Let me show you all group 1s. I'm going to put it in black here. I'm going to make it a little bigger for you. This is a group 1. That's a group 1 right here. Those are group 1s. These are group 2s. Those are 2 horrible lines. This is group 1. This is group 2, which means all of those ions are inside that, because it says right here, group 1 and group 2 are all inside that. Well, Mr. Pepik, what about silver? Is silver in this box? Well, is silver in group 1? Is silver in group 2? No. Is silver ammonium? Nope. Then silver, ladies and gentlemen, would be in this box. I'll make that red for you. Silver's in here. Everything would be inside this box, whether it be nickel, cobalt, iron. How do you know they would be inside this container here, this side? Because they're not in that one, which means all of those would be insoluble. Okay, so hopefully this makes sense. So we'll go through a couple of examples. If you mix calcium with hydroxide, will that be soluble or insoluble? Well, the calcium's on this side here, and the hydroxide, which means it's going to be on the soluble side. Let's take a look at another one. What if we would mix iron? If I put iron with hydroxide, is iron any of these in here? Or is iron in this box? Nope. Then iron must be in that box, which means iron 2 hydroxide is going to form an insoluble compound. So either we're moving to the right or we're moving to the left. That's the only trick to using this chart. So we're going to do some examples right now. Hopefully I explained myself well. Not being in class could cause some problems, but I'm here to work with you. So let me hurry so that this video doesn't take like 3 hours. So here we go. Our homework is to take these cations, which are pluses, and these anions, which are negatives, and put them together and try and figure out whether they're going to be together in solution or apart in solution, whether they're going to be insoluble together, a solid, or whether they're going to break apart and be soluble or aqueous in solution. So let's take a look. First one we have is sodium and acetate. So here's acetate up here. There's our acetate. And we want to put it with sodium plus. Is Na plus in this box right here? Is Na plus in that box, ladies and gentlemen? No? Well, then Na plus must be in this box. And Na plus is going to be soluble. So how are we going to work this out? You'd come down here and say this one's going to be soluble. We're going to put an X, and we're going to write the formula Na and then CH3 COO. And that's it. Let's do the next one. Iron 2 plus and iodide. So let's take iron 2 plus and iodide. So here's iodide right here. I'll change the color. Okay, let me make it green. So we're working here now with iodide, and we want to put it together with Fe2 plus. Is Fe2 plus in here? I'm not sure. So let's look on the other side. That's not Fe2 plus. That's not Fe2 plus. That is not Fe2 plus, and neither is that, which means Fe2 plus, iron 2 plus must be in the soluble side. So that must be a soluble compound. So we're going to come down here and we'll say this must be a soluble compound. Boom. And then let's write the formula. There's one Fe and two iodides, which means it's going to be FeI2. Let's take a look at another one. Let's change the color. Let's make this one brown. All right, so we're working with iodide again. So here's our iodide, right? Here's our iodide. And now what are we mixing with it? We're putting lead with a 2 plus charge. Let's see, is lead 2 in this box? I'm not sure. Let's look over here. That's not lead 2 plus. There's lead 2 plus. So that means that lead 2 plus and iodide are going to react together. If you move in this direction, you're moving towards the insoluble side. And all of a sudden, we know that's going to be insoluble. So this one will be insoluble, which means it stays together. We need to come up with a formula. We have 2 plus and a minus 1. So we're going to need 2 of those iodides to balance that out. Let's go to the next one. Let's make that one pink. So now we're working with NO3. Let's go to NO3. Where's NO3? There's nitrate, NO3 minus, and then we have silver. Let's see. Where is silver? Is silver in this box? Not sure. All cations are in this box, which means silver plus must be in that box, which means these two are soluble. So this will be in the soluble column. When we're going to make the formula, which is going to be an Ag with a +1 and NO3 with a -1, so it's just going to be AgNO3. All right, let's move down to this one here so I can move to the last assignment. I guess I'll keep it pink. What the heck? So let's take a look. We'll look at barium and hydroxide. Oh no, you know what? We won't do that. Let's just do this one here. Let's look at copper and sulfate. All right, so here's sulfate. And we need to find copper. Is copper in this box? I'm not sure. Almost everything's in there. So let's see if it's in there. Is that Cu2 plus? Nope. Is that Cu? Nope, 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 nope. Is Cu2 plus in this box right here? That's right, it's not. Cu2 plus must be in that box, which means when these two react, it's going to be going towards the soluble side. And I'm going to put soluble right here. And then I'll write the formula, which is a 2 plus with a 2 plus, Su, a CuSO4. Okay. And now lastly, let's go to barium hydroxide. So here's barium hydroxide. I guess I'll go back to green. All right. So here we have hydroxide. Okay. Now let's find the barium. Where's barium? Is barium in here? We don't know. Let's see. Is this barium? NH4 plus? That's not barium. Is barium in group 1? I don't think so. Is that barium? Nope. Is that one? Oh, yeah, there it is. Super. So those two are together, which means moving to the soluble side, and we're done. Hopefully, I did a good job explaining this, ladies and gentlemen. We're almost done. So we put here, this one would be soluble, and the formula would be Ba, which is a 2 plus. OH is a -1, so we're going to need to put parentheses, keeping it together, and putting down 2 of those. All right, so let's move on over this way and show you the second part of your homework. Now, when we're working with formulas, I'm not always going to sit there and be like, oh, it's a +1 or a +2. You're going to have to figure that out on your own. And so let's take a look at this first example. We want to find silver chloride and figure out, will silver chloride dissolve and be soluble, or will it stay together and be insoluble? So let's find silver chloride. Well, here's the chloride. Now, my suggestion is to always look for the negatively charged one, which always comes second. And now we want to see, is the silver in this container here? I'm not sure. So let's look over in this one. Oh my gosh, it's right there. First one. Then, boom, we're moving in this direction towards the insoluble side. Silver chloride is going to be insoluble. So I'm going to write the word insoluble there. Insoluble. I don't know why. There should be another column here. I'm going to add it really fast. All right, so there, when you do your homework, there's going to be another box that says, what are the ions if present? There are no ions here, so you just leave it blank. Let's go to barium sulfate. So down here, this is barium. This is barium. This is sulfate. Okay, so let's look at sulfate. Let me change the color. We'll go to green. So here is sulfate. We're working with sulfate, right? Now we have to find barium. Is barium in the soluble side or the insoluble side? Oh, there it is right there. Barium sulfate is insoluble. So you would write insoluble here. And then over here, you might just write none. All right. So next one, magnesium sulfide. Let's go find magnesium and sulfide. Let's change that color so we can see it. So we always look for the negatively charged anion first. There's sulfide. Now we have to find out, is magnesium in this box or in this one? This one has most. So let's see if it's in this one. Is this magnesium? Nope, that's not magnesium. And let's see, is magnesium a group 1? I'm not sure. Let's find out. Where was I? Oh, wait, was it not? Did I take it out? Let's go get it again. I must have gotten rid of it. Should have been up there. So there's our compound. This is our periodic table. Here's magnesium right here. Is magnesium in group 1? Nope. Is magnesium in group 2? Yes, magnesium's in group 2. So everything, instead of me writing all of the ions here, I just put group 2, which means magnesium 2 plus is in this box. We're going to move in this direction, which means we're soluble. All right. And soluble, let me come back to my document. All right, soluble right here. Right. All right, soluble here. S-O-L-U-B-L-E. Since it's soluble, that means it breaks apart. And in this box, I need you to write, there's going to be an Mg with a 2 plus charge. And also, there's going to be an S with a 2 minus charge. And so that's how we're going to work that one out. All right. So for this last one, we'll look and see. Whoopsies. We'll look and see. We have lead and hydroxide. All right. So let's change the color to this brown color. So we have lead and hydroxide. Let's look for the hydroxide here. There's hydroxide. And let's find which box is lead in. That's not lead. Is lead in group 1? Let's go and look. Is lead in group 1? I think that was it right here. Let's see. Nope, there's lead right there. Lead is not in group 1. So now let's go take a look. Let's go back to our document. Lead is not in group 1, which means that lead must be over here, this lead 2, this PB2. So that means, whoops, wrong box. Sorry, down here, PB2 plus, which means these two are going to be together, which means insoluble. So now let's come back over here and write insoluble. Insoluble. We're going to come on across, and there are no ions present because it's insoluble. Now, something that I put over here, we're going to get to this next class. We're going to start looking at things that's going to say AgNO3 aqueous, NaCl aqueous yields. And so we're going to start seeing this more, and we're going to be drawing pictures next class. But today, you're just trying to figure out if you can tell if something is soluble or insoluble by using this chart. If you have any questions, please let me know. I'm sitting right here. I hope you guys understood everything. If you didn't, hey, give me a holler. I'm trying to keep it real. Have a great day, kids. Let me know if you need anything. Oops.